There are two basic types of fractures, ductile and brittle. The ductile fracture undergoes an appreciable plastic deformation before actually breaking apart. Plastic deformation is permanent deformation, as opposed to elastic deformation, which will spring back to the original shape when the load is removed. Brittle fracture occurs without appreciable plastic deformation. These two terms, ductile and brittle, are usually applied to single overload fractures. Multiple load fatigue fractures also exhibit little or no macroscopic plastic deformation prior to fracture, so they too can be considered brittle. The terms ductile and brittle refer basically to the behavior of the metal. A ductile metal is relatively soft and, as already defined, can often undergo considerable plastic deformation before fracturing. Soft steels, solder, copper wire, and aluminum foil are ductile. During manufacturing, ductile metals can be subjected to extensive forming operations, such as bending, stretching, compressing, twisting, and deep drawing, without rupture or cracking. Brittle metals, on the other hand, are likely to break with this kind of treatment. Very hard steels and gray cast iron will crack or fracture without showing any significant plastic deformation in such cases. Ductile and brittle actually represent two extremes of metal behavior, as opposite as black and white. But just as there are many shades of gray in between, so too many metallurgical conditions can make a metal partially ductile or partially brittle. That is, most metals show intermediate ductility, unless they are deliberately made to be very ductile or very brittle. Incidentally, the term metal in this program is used to denote all metal-base alloys. Fundamentally, there are only two types of single overload fracture: shear and cleavage. Shear is typical of ductile metal fracture. Cleavage is a brittle fracture, referring to the brittle behavior of the metal. Actually, shear and cleavage refer to the behavior of the metal on the atomic scale within the crystal lattice, the name we give to the orderly arrangement of atoms. In many metals, these arrangements could be described as rows of cubes. We call these cubes unit cells, and the lattice a cubic lattice. If a metal is fractured by a single load, the break can occur one of two basic ways: across the face of the unit cell, separating the cell from the adjacent unit cell, or the break can occur through the diagonal plane between the atoms of the cells. The term shear literally means slide. When the parallel planes of atoms in a cell or crystal slide across each other, the movement on this atomic scale is called shear. A small degree of shearing movement normally occurs in the elastic range. As long as the loading remains in the elastic range, the movement is reversible and the atoms will revert back to their original position when the load is removed. But there is a limit to this elasticity. If the elastic limit of the metal is exceeded by the load, the atoms are forced to slide to new locations. This movement is irreversible, and the metal is now permanently deformed by yielding or plastic deformation. The elastic limit of the metal has been exceeded. The cumulative effect of this change is plastic deformation. When we test to quantify this total effect, we refer to it as ductility. Cleavage on this atomic scale means splitting. A very rapid split or separation of the crystal lattice could be expected along a side or a face of the cell. This cleavage fracture occurs before yielding and permanent deformation can occur. Cleavage is a brittle fracture. Actually, cleavage is only one of two different brittle fracture mechanisms. The other, known as intergranular, will be discussed later in the program. For now, it's easier to consider only shear and cleavage as the fundamental types of single overload fracture. Shear and cleavage are quite different in many ways. The movement of shear is sliding. The movement of cleavage, splitting. The rate of fracture in shear is generally slower. In cleavage, faster. With shear, there is deformation. With cleavage, no deformation. Shear is typical of ductile metals, cleavage of brittle metals. Generally, a tensile fracture that has sheared appears dull and fibrous. Cleavage fracture is usually bright and sparkling. Certain factors will affect the ductile-brittle relationship in metals. These factors indicate the trends most likely to affect the behavior, particularly in metals such as iron and steel, which have a cubic crystal lattice. Temperature. At high temperature, ductile behavior is more likely. At low temperature, brittle is more likely. When the rate of loading is low, ductile behavior is more likely. When high, brittle is more likely. When the geometry of the metal is without a notch, ductile behavior is more likely. With a notch, brittle is more likely. Generally, when the tensile strength and hardness of the metal are low, ductility is more likely. When high, brittle behavior is more likely. Sometimes metals do not behave according to the indicators. Gray cast iron, for example, a very common metal, has relatively low strength and hardness, indicating that it should fracture in a ductile manner. But gray cast iron always appears to fracture in a brittle manner. The reason for this strange behavior is the geometry factor. A large number of internal notches are inherent in gray cast iron. These notches are in the form of very thin graphite flakes. And according to the indicators, notches indicate a trend toward brittle behavior. In reality, the notches override the strength and hardness factors. Hence, cast iron with low strength and hardness appears to fracture in a brittle manner. On a microscopic scale, however, gray cast iron still behaves in a ductile manner between the graphite flakes. Gray cast iron is an important exception to strength and hardness as indicators of the trends most likely to affect behavior in metals. Ductile fracture. One of the first things to look for in a fracture is distortion. Distortion is usually an indication of ductile fracture. But sometimes there are questionable cases when little or no distortion by plastic deformation is present, as observed at low magnification. In these cases, an electron microscope can be used to study the characteristics of the fracture surface itself, assuming that the surface is in a suitable condition. Magnified up to 10,000 times in the electron microscope, the surface of a ductile fracture shows a characteristic mass of half microvoids. These are called dimples. When overload is the principal cause of ductile fracture, most common structural alloys fail by a process known as microvoid coalescence. Tiny cavities form at regions of localized strain, such as that associated with foreign particles, inclusions, and grain boundaries. As the strain in the material increases, these microvoids grow in size and begin to join together or coalesce. Eventually, these coalescing microvoids join to form a continuous fracture surface known as dimple rupture. The sequence of events leading to fracture in a ductile metal begins with necking down of the specimen to which a tensile force is applied. As the specimen necks down, the fracture initiates internally with the formation of microvoids in the necked region. These microvoids grow or coalesce to produce an internal crack. The final separation of the cross-section occurs by shear rupture. The fracture has a characteristic cup and cone appearance after the necking down, and the final rupture produces a shear lip, which forms the wall of the cup. With an SEM, a scanning electron microscope, the fracture surface of a dimple rupture exhibits tiny cup-like depressions. These are the dimples, which are the microvoids torn apart during the rupture process. The size of the dimples on a fracture surface is governed by the number and distribution of microvoids that are formed. When these nucleation sites are few and widely spaced, the microvoids grow to a large size before joining. The fracture surface then contains large dimples. When many microvoids are formed and adjacent microvoids join before they have an opportunity to grow to a large size, the fracture surface contains many small dimples. The shape of the dimples is governed by the state of stress within the material as the microvoids form and coalesce. Under conditions of uniaxial tensile load, which applies a generally uniform strain across the section of metal, the resulting fracture essentially forms equiaxed or round dimples. Depending on the microstructure and the ductility of the material, the dimples can exhibit a very deep conical shape, or they can be quite shallow. The shape of the dimples can vary with the mode of stress applied to the metal. A tear fracture, applying a tensile stress at any end and tearing the metal, may exhibit elongated dimples. The dimples are elongated across one axis, and the end of the dimple is open. That is, the dimple is not completely surrounded. In the case of a tear fracture, the elongated dimples on both fracture faces are oriented in the same direction. The closed ends of the dimples point to the origin of the fracture. This characteristic of tear dimples can be used to establish the direction of fracture propagation. A torsional shear fracture, however, exhibits elongated dimples that point in opposite directions on the mating fracture faces. Sometimes the slant fracture or shear lip of the ductile fracture resembles a picture frame on a relatively thick rectangular section. The shear lip shows that the fracture emerged from the interior of the metal at that location. Surface failures caused solely by ductile fracture are relatively infrequent. When they do occur, the structure or machine component is often stated to have failed as the result of a single overload, as from an accident. Single overload failures may be the result of a part having been under-designed for a specific set of service conditions. The design of parts includes the selection of materials and their heat treatment, so these factors too can be implicated in the fracture. The parts may be improperly fabricated or fabricated from defective materials. Fracture may be the result of the part having been abused, that is, subjected to conditions of load and environment that exceeded those of the intended use. Forces generated in an accident, for example, are a violent form of abuse and can be extremely high. Here is a simple example of ductile torsional fracture of a machine component. A rear axle of a race car fabricated from an AISI S7 tool steel fractured as a result of a torsional or twisting overload. The deformation marks around the smaller diameter section of the shaft show the effects of twisting by the high input torque. The cause of the failure was improper hardening of the shaft. Before going on with ductile to brittle and brittle fractures, let's review some of the important points about ductile failures and their causes. Ductile fractures differ from brittle fractures in that they usually undergo appreciable plastic deformation before actually breaking. A ductile fracture is typically a shear fracture. Shear is the sliding of the atomic planes in the crystal lattice of a metal. A tensile fracture that has sheared appears dull and fibrous. When overload is the principal cause of ductile fracture, most common structural alloys fail by microvoid coalescence. Coalescing microvoids join to form a fracture surface of microscopic dimples. A ductile fracture on a microscopic scale is a dimple rupture. Certain factors affect the ductile-brittle relationship in metals. Metals are more likely to tend toward ductile behavior when the temperature is high, when the rate of loading is low, when the geometry is without a notch, and when the strength and hardness are low. Ductile to brittle transition. Some metals undergo a ductile to brittle transition in their fracture behavior at low temperatures. Fractures arising from ductile to brittle transition have an especially insidious character. They may occur without warning, and they may occur under static loading at stresses well below the nominal yield strength. This brittle fracture is induced in certain relatively ductile metal by low temperatures or impact and is usually associated with notches. The ductile to brittle transition can be demonstrated quite readily by the Sharpie V-notch impact test. The results of tests conducted on a low-carbon steel show the drop in absorbed energy as the temperature decreases. The transition from ductile to brittle fracture is made visible by a decrease in the amount of lateral expansion on the compression side of the specimen. The shear lip is reduced as the test temperature decreases, and the appearance of the fracture surface changes from a rough ductile fracture to a relatively smooth, flat, brittle fracture. At temperatures within the transition range, crack propagation occurs by both microvoid coalescence and quasi-cleavage. This new term refers to fractures that exhibit a rupture between brittle and ductile, with the appearance of mixed dimples and cleavage. The quasi-cleavage is predominantly confined to the central region of the fracture surface. Brittle fracture. Brittle fractures in service are frequently initiated at stress concentrations that are present in the structure of the manufactured product. Discontinuities that develop during service can also initiate brittle fracture. The initiation area, strongly influenced by stress concentrations, may take any one of 5 forms. First, notches. Notches are discontinuities caused by abrupt changes in the direction of a free surface. Among the common intentional notches are sharp fillets and corners, holes, threads, splines, and keyways. Notches can be produced accidentally. Mechanical damage, such as dents, gouges, or even scratches, can start brittle fractures. And notches can also be produced by sharp contour changes created as a result of poor welding practice. When fracture occurs, it initiates at a notch. It makes no difference whether the notch is intentional or accidental. The radial marks on this fracture surface converge at a surface scratch that initiated the fracture. The second form of initiation area results from laps, folds, flakes, large inclusions, forging bursts, laminations in sheet and plate, and undesirable grain flow introduced during working operations. All these may influence the location of fracture origin. Third, factors causing stress concentrations may lead to failure. Certain discontinuities, such as segregation, inclusions, tears, cracks, porosity, and shrinkage cavities, can have serious consequences, particularly in castings. Fourth, cracks resulting from machining, quenching, fatigue, hydrogen embrittlement, liquid metal embrittlement, or stress corrosion also lead to brittle fracture. In fact, the single most prevalent initiator of brittle fracture is the fatigue crack. The fatigue crack accounts for at least 50% of all brittle fractures in manufactured products, and this is a conservative estimate. The fracture surface of an ASTM A36 structural steel member shows this failure began with a fatigue crack, which progressed only a short distance before brittle fracture occurred. Finally, residual stresses. Residual stresses are not defects in a geometric sense, but they can be an important factor in the initiation of brittle fractures. Here is a brittle fracture that originated from residual stresses at a hole punched in a steel plate. The chevron pattern is evident on the mating halves of the fracture, pointing back toward the hole. In such situations, moisture may have had access to the hole and contributed to the formation of the initial crack. Residual stress effects are most important in hard, strong metals. Softer, weaker metals can deform and relieve the residual stresses. Cleavage, the basic brittle fracture mode, is a low-energy fracture that propagates along well-defined crystallographic planes. These are known as cleavage planes. As mentioned earlier, cleavage is only one of 2 different brittle fracture mechanisms. The splitting cleavage along the crystallographic planes is transgranular. The cleavage occurs through the crystal grains. The other type of brittle fracture is intergranular. Intergranular fracture occurs between the crystal grains of the metal through the grain boundaries. This is due to a variety of mechanisms that make the grain boundaries weaker than the grains themselves. The grains of a metal can be compared to bricks in a brick wall. The mortar between the bricks would represent the grain boundaries. An intergranular fracture would occur between the bricks through the mortar or the grain boundaries. A cleavage fracture, transgranular, occurs through the bricks, through the grains themselves. Theoretically, a cleavage fracture, that is a brittle fracture, should have perfectly matching faces. On a macroscopic scale, the surface should be completely flat and featureless. However, engineering alloys are polycrystalline, composed of many crystals or grains. They contain grain and subgrain boundaries, inclusions, dislocations, and other imperfections that affect a propagating cleavage fracture, so that true featureless cleavage is never observed. These imperfections and changes in crystal lattice orientation produce distinct cleavage fracture surface features. They are seen as cleavage steps, river patterns, feather markings, and tongues. The cleavage fracture frequently initiates on many parallel cleavage planes. As the cleavage fracture advances, the number of active planes tends to decrease by a joining process. The planes join to form higher cleavage steps. This network of cleavage steps is known as a river pattern. Because the branches of the river pattern join in the direction of crack propagation, the marking can be used to establish the local direction of the fracture. Feather markings are a fan-shaped array of very fine cleavage steps on a larger cleavage facet. The apex of the fan points back to the fracture origin. Tongues are occasionally observed on cleavage fractures. They are formed when a cleavage fracture deviates from the cleavage plane and propagates a short distance along a twin orientation. Fracture by mixed mechanisms, the gray area, is generally labeled a mixed mode fracture. The fracture surface exhibits intermingled features of two or more mechanisms of fracture in a given area. This mixed mode fracture should not be confused with a fracture surface showing features that suggest the successive operation of different fracture mechanisms as cracking proceeds across a section. In this case, the individual fracture mechanisms can be analyzed sequentially. In mixed mode fractures, the various mechanisms are truly intermingled. The state of stress, loading history, microstructure, and environment can create conditions in which two or more mechanisms or fracture modes can operate simultaneously. The second type of brittle fracture, intergranular, is easy to recognize, but its cause is much more difficult to identify. The surface of an intergranular fracture, most often, initially appears bright and sparkling. It is characterized by a rock candy appearance, easy to recognize in electron microscope examination. The cause of an intergranular fracture is difficult to recognize because the complexity is promoted by the cumulative effect of environmental factors and sustained stress, by grain boundary embrittlement, and by impact loading. Steel is not the only metal that encounters brittle fracture, but steel, a primary metal in many industries and products, is faced with a variety of potentially serious brittle fracture possibilities. Many forms of embrittlement of steel parts can lead to intergranular brittle fracture. At least 9 forms of embrittlement can occur during thermal treatment or elevated temperature service. Strain age embrittlement in low carbon steel. Quench age embrittlement in low carbon steel. Blue brittleness in some carbon and alloy steels. Temper embrittlement in constructional alloy steels. Tempered martensite embrittlement in high-strength, low-alloy steels. Stress relief embrittlement in weldments. 400 to 500 degree embrittlement in ferritic stainless steels. 4 to 500, by the way, is centigrade. In Fahrenheit, the embrittlement occurs between 750 and 930 degrees. Sigma phase embrittlement in high chromium steels. Graphitization in carbon and low-alloy steel high-temperature piping. And intermetallic compound embrittlement in galvanized steel. In addition, steels and other metals and alloys can be embrittled by environmental conditions. Most prevalent are hydrogen embrittlement, stress corrosion cracking, and liquid metal embrittlement, which will be discussed in another program. This is not all that can be said about the causes of brittle fractures. The subject is far too vast and complex, with far too many interrelated factors to be covered in one program. In summary, then, these are the basics of brittle fractures. The basic brittle fracture mode is cleavage, a low-energy fracture that propagates along well-defined crystallographic planes. Cleavage is transgranular through the grains. The second type of brittle fracture is intergranular, through the grain boundaries and between the grains. Cleavage fractures produce distinct surface features, river patterns, feather markings, and tongues. Cleavage fractures appear bright initially. Intergranular fractures appear bright and sparkling like rock candy. Intergranular fractures are promoted by the cumulative effect of environmental factors and sustained stress, or by grain boundary embrittlement resulting from a number of different metallurgical phenomena. Many forms of embrittlement can lead to intergranular fracture in steel. Most often, the initiators of brittle fracture are discontinuities, notches, and stress concentrations. Failures from improper fabrication are caused primarily by the imperfections produced in parts during processing. These can lead to either ductile or brittle fractures. Many of the interrelated factors causing brittle fractures cannot be covered in a single course. In fact, the entire subject of brittle fracture is so vast and complex that many of the finer details are covered in other programs in this series on failure analysis. This lesson is only the beginning.